Hi everybody, this is Mr. Pauli, and this podcast has a ton of slides to it, so I want to just hop right into it. See, it looks like it's short just by the look of it, but it's got a lot of slides, so I'm going to go right through these things. This is the first slide I might make sure I read from everything to do. You need to absolutely memorize these list of flame tests. We talked a couple of times about the flame test before. If you burn copper ions in solution, so if you have a copper solution, you put, say, copper, guess what, copper nitrate, or lithium or strontium nitrate, you can tell the different colors. So one of them is green, copper is green, lithium and strontium are red, sodium is yellow, barium is yellow-green, and potassium is violet-pink. I'll show a YouTube clip, or actually I'll probably just set those things up and show you how they work. I like the YouTube clips better because I think the color is a little more distinct, and I'm a little colorblind to begin with. So the reason why you get these things is electrons jump, fall, and emit different colors of light. And the reason why they have these different jumps and these different falls is because their sizes are always a little bit different. So depending on the size of the nucleus, the distance here would be 2, and distance here would be, just say, 5, and the distance here would be, let's say, 11. And if you have a different element that's just different in one proton, the differences would be, say, 3. Well, 3 to that one. And then this could be 6, and then this could be 14, or something even more bizarre. So those things change, and that's it. You do need to have a basic idea of the different kinds of electromagnetic waves. Electromagnetic waves are often just light, but it's not just light. There's gamma rays, right? That's the most powerful one. When I think of the most powerful superhero there is, it is the monstrosity of the Hulk, which I thought I clicked on green, but I apparently didn't. So the Hulk with his big beastly self. Look at the muscles on the Hulk. Although, right now, he looks like he's got a pot belly. Oh, what have I done to the Hulk? Anyway, at least I can give him a 6-pack or 4-pack or whatever it is. But, great, the Hulk looks like an old lady in a moo-moo. But anyway, the highest energy makes the strongest superhero. Okay, you know visible light isn't that harmful. And you especially know that radio waves are not that harmful. We're being constantly bombarded with radio waves. That's why we can pick up radio stations so easily. And no one says, oh, look out, we're all going to get cancer from radio waves. No, we are perfectly safe from radio waves. As you start to go to the left, they are more and more and more and more dangerous. This microwave here is in the wrong spot. Sorry about that. So we have radio waves, and then as we move from the weak radio waves to a little bit stronger, we have infrared. And then we have visible light, which is Roy G. Biv. Infrared is basically heat. People don't freak out about heat, but people do know that UV light causes skin cancer. I shouldn't be using green anymore. UV light causes skin cancer. So you know that's dangerous. You also know X-rays are dangerous because your dentist steps out of the room when they shoot you with your little X-ray machine. So you don't want to get you don't want to get 50 X-rays a day. You don't want to get 50 gamma rays ever. And UV is the sun. You can go out in the sun, get a little bit tan before you get skin cancer, and then shrivel up and keel over. I want to remind you, since talking about electrons jumping up and down and releasing energy, we've got equation sheet fun. So when you look at the atomic structure thing, we still have to remember E equals h nu, blah, 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 blah. Exact same slide you saw earlier. More electron history. Einstein said electromagnetic radiation, remember that's everything from gamma rays through radio waves. And which one's strong again? Hulk smash. Which one weak again? WKRP in Cincinnati. He said electromagnetic radiation is quantized in particles called photons. So that means they were all or nothing little bundles. So you're either going to get hit with a little BB or you're going to get hit with a cannonball. There's nothing in between. There's either a BB or a cannonball. Or they're actually distinct ones. There might be things in between. You know, you might get hit with a slug of, I don't know, the other slug sizes, but you get the idea. Each photon has an energy. Energy equals h nu. Or, because we can figure out that nu is c over lambda, energy equals hc over lambda. You can combine this with equals mc delta T, and you can get the apparent mass of a photon. So let me show you where this is coming from. Energy equals hc over lambda. E equals mc squared equals energy. So that means I can say hc over lambda equals mc squared. So what happens here is a c cancels out, right? So I have m equals h over c lambda. Okay. So h is a very small number, 10 to the negative something big, it's something like negative 34. You're dividing it by, well, let me do this. So e to the negative 34 divided by e to the 8th divided by, I don't even remember what your lambdas tend to be pretty small too, like e to the negative 6, say. So you're going to be a very small mass of a photon. So this means that energy has mass. So is energy a wave or is it a particle? And in reality, it's kind of both. The concept is called the wave-particle duality. You need to know that it's both. What about the other way around? Is matter a wave? Here's how we test to see if matter is a wave. When light passes through or reflects off a series of thinly spaced lines, it creates a rainbow effect because the waves interfere with each other. In your book at 7.5a, I'll draw a cheap representation of it right here. Okay. So if I've got a series of lines going through here, what happens is if I have a wave, I'm going to have to use black, I'm sorry, as it approaches this thing, because waves are, and this is one thing, so it's really moving ones together, because waves are flexible or whatever you want to call it, it can create little humps like that happen. And then as that moves on, maybe red will work a little better here. Boom, boom, boom. I now have places where these things have intersected. Okay. And where they intersect, you then get a rainbow effect where you can get the interference. Constructive interference would be a bright spot. Destructive interference would be a dark spot. So again, we're thinking about electrons. So we think electrons are particles. Oops, let me use my black one again. We think of electrons as particles. So that means if I shoot particles at something, it's either going to go through, whee, or it's not going to go through. Aww. Right? Those are the two choices if it's a particle. If you shoot electrons at something and you start to get interference patterns, constructive or destructive interference, you know that electrons are waves. I guess I had some slides that show this. A wave moves towards a slit. Woo! The whole thing moves, right? It moves all at once. And comes out as a curve. This is what happens with a wave. With two holes, you would get two curves. All right? All right. And then as time moves on, these would become larger and larger. And the blue ones would also become larger and larger. And you would be able to tell what's happening by looking at the interference pattern. So particles cannot have an interference pattern. However, waves can. What will an electron do? It has mass, so it's matter, so that means matter is a particle. A particle can only go through one hole. A wave goes through both holes. How do we know this? Because we have an interference pattern. An electron does go through both and makes an interference pattern. It behaves like a wave. But we also know that it is a particle. Other matter has wavelengths too short to notice. So remember, using that Einstein equation, we could figure out if we could figure out the mass of things like a photon, we could figure out the wavelength of things like a baseball. And if a thing like a baseball has a wavelength, you can think of it as going. So imagine if you're standing up here with a baseball bat, I suppose you put two hands on your bat, trying to hit a baseball, and it's moving up and down like that, it makes it much more difficult, especially if it's going up and down the way I have it drawn, looking like 2 feet at a time. However, the wavelength, it says too short to notice, really is too short to notice. So you're talking about wavelengths in the neighborhood of negative e to the negative, I'm going to say 40 meters. So small you really won't notice. Graph showing where electrons hang out. I forgot what I was doing with this. Hang on a second. Oh, now I know where I was going with this. I can look at the probability curve of where electrons are. So I can look at the probability. This would be a high probability of 100%. This would be 0%. Places that are 0% probability of existing are called nodes. So if you have a 0% probability of being somewhere, it's called a node. It means you're not going to be there. So if I then take the sum of all of these probabilities, I get these weird shapes. And from these weird shapes, we can then figure out where the electrons possibly are. So the Pauli exclusion principle says no two electrons can exist, no two electrons in the same atom can have the same set of 4 quantum numbers, which means 2 electrons can't occupy the same space at the same time. And then this is my interpretation. Duh. Okay, so 2 things can't be in exactly the same place at exactly the same time. You cannot be in exactly the same place at exactly the same time as Oprah. You cannot occupy the same chair as Oprah at the same time. Believe me, Oprah will take up that entire chair, and you will not be able to sit there. How sad. So what this really means is we're going to have clouds of electrons where 2 electrons can exist at a time. S orbitals look like spheres. P orbitals, they say, are dumbbell shaped. I don't get the dumbbell things. They call that dumbbells. Just realize they say it's dumbbell shaped. It's a p orbital. D orbitals, they say, are complex. I don't think that's very complex. I don't think that's very complex. I keep saying complex. What's wrong with me? Very complex. This, I think, is the coolest orbital I've ever seen so far. And then you see F orbitals, and you see some of these freaky things. Now, this is an orbital. So if I asked you, if I drew a picture of this and said, how many electrons are in this area I've just circled? It is not 2. Okay, this whole orbital, this whole thing I've circled right here, holds 2. Okay, so not just this little nugget right here, not this little donut-looking thing right here. The whole thing is an orbital, so it holds at most 2 electrons. So does that mean that 1 electron is here, and then another electron is here? No. They are in either one of those. And remember, electrons cannot exist in these nodes. Notice how there's no space right there. That means an electron is here, and then it is here, and then it is here, and then it is here. It is never in between. Now you know why sometimes I wonder if I really believe in atoms. More F orbitals, just looking all crazy. Penetration. There are levels to the electron distribution for each orbital. So this is the 2s, and it's got different things where the electron is going to be more likely to be. This picture, I suppose, I don't like all that much, except for it looks like a bullseye. So there are levels to the electron distribution for each orbital. The levels referring to how close you are to the nucleus and how far away from the nucleus you get. Graphically, you know, most of the space for 2s is over here. This is most of my 2s. Whee! But there is some over here, right? So this is closer than expected. Notice again, this probability is 0. So an electron can go here, whoop, all the way over here. That's what S does. D, well, you can see what's going on here. I chopped some of these things out. So this would be 3s, this would be 3p, and this would be 3d. Notice how S has the highest amount close to the nucleus. The closer an electron is to the nucleus, so a close electron to nucleus equals strong bond which equals what kind of energy? Low energy, because energy is going to be released, which means it's favored. So whatever has the most energy, or the most probability of being closer to the nucleus, is going to be the lowest energy. So according to whose principle? Aufbau's principle. You fill the lowest energy first. So what makes the s orbital the lowest? It has the most penetration. So it will be closer to nucleus. So it will be, of course, lowest energy. And then the next lowest would be the p orbital, then the d orbital, and then the f orbital. And I think I just answered my next slide. Which has more area closest to the nucleus? 4s or 3d? Notice this area right here is the most. So 4s does. So 4s is filled before 3d. To review. Yay. Memorize your flame colors. What's copper again? Green. What are the other ones? I forgot. But you better not. Gamma is dangerous. Radio waves are not dangerous. And you need to know light's place in the null, meaning light is in the middle. And you need to know Roy G. Biv. Roy, red, is closest to infrared, which is a lower energy. And violet is closer to UV, which is ultraviolet, which is higher energy. And just think about things that you don't really want to expose yourself to. When I worked at the car wash, there was a guy, his name was Eugene. And it was just like this, and he said you had to pronounce it Eugene. And this was back in the day when we had really old microwave ovens, and he used to warm himself up by, you take your little microwave oven, and you'd open the door. I wish I would have taken a drawing class. And what Eugene did was Eugene stuck his hands, both of them, in the microwave and turned on the microwave before it had safety devices to stay warm. Eugene disappeared sometime later. He was also the guy who ate roadkill, but who knows what happened. But I didn't do that, and I'm still here so far. So, electrons are waves and particles, as is everything else. A graph of the sum of all probabilities shows the shape of the of the shell, which is the L quantum number. Remember, N is the row, L tells us the block, and the block really tells us the shell, which really tells us the shape. Define penetration as a relationship to Aufbau. The more penetrating a shell is, the closer to the nucleus. The stronger the bond, lower the energy. Remember, if you have, people say that people that are married live longer, and I think it's because they have a wonderful bond with the person that they're married to. So they are lower energy, they get to live longer, and live happily ever after. Aw, so I wish you a happily ever after until I see you in class tomorrow. See you then. Bye.